Imagine a giant vacuum cleaner, but instead of dust, it pulls out the CO2, the carbon dioxide, out of the air. It sounds like science fiction, but it's not. It's called direct air capture, or DAC. And today, there are plants that are running that way in Iceland, Texas, or California. But I wondered, how does it actually work? Also, are those companies scalable? And how much does it cost compared to how much does it bring to the environment? This is a series of 3 episodes that I'm gonna do about the actual technology, the scalability of the technology, the business model in the second video, and finally deep dive into some of those companies and see how they work. Are you ready? Let's go. So the first step is move the air. Why? Because CO2 only constitutes 0.04% of our atmosphere. So we need to move a large portion of air through a big fans to be able to capture the CO2. The second step is capture the CO2. This is where the magic happens. It's where the CO2 is extracted from the air. There are actually 4 types of filters that we'll go through just after: solid, liquid, mineral, and electrochemical. The third step is actually release the CO2. We move the air into our sponges. Our sponges absorb the CO2. Now we need to release it. We release the CO2, so can we store it in underground or use it. So now let's dive in directly into the 4 techniques to actually capture the CO2. So we have now currently the state of the art discovered 4 ways to capture the CO2 out of the air. Those 4 ways are like this. The first one is the solid sorbents. So companies like Climeworks in Iceland have developed this technology. They use low temperature heat and sip on water. The problem is that the filters wears out after a certain time, so you have to change the filter every now and then.
There's another natural way to absorb CO2, mineralized inside rocks. This natural process can also be imitated and accelerated using a specific technology. At Climeworks, we capture CO2 from the air for it to be stored deep underground by our partner, CarbFix in Iceland. CarbFix takes our captured CO2, mixes it with water, and injects it at least 800 meters underground into basaltic rock, where the CO2 solidifies and can no longer contribute to global warming.
Then the liquid solvent company like 1.5 in Texas have developed this thing. The good thing is it scales massively using liquid alkaline, but the problem is that they use temperature close to 1000 degrees. So that means that it requires a lot of electricity to actually heat up the process. Third way is actually mineral looping. So mineral looping means that we have cheap rocks that we can put in the process that capture the CO2. But the problem is that they need land and time to actually filter out the CO2. So it's effective, but it's quite long. And finally, the last technique is electrochemical. There is a lot of advantage because it doesn't require a lot of heat, and it's also very scalable and all electric. But the problem is a very early stage. Only companies like Verdox and Mission Zero have developed them, and we're still in pretty early stage of those technologies. why are we talking about direct air capture in 2025? Why no one talked about it in 1975, 50 years ago? So the first reason is actually the available clean power. It wouldn't make sense to run any of those facilities on coal. If you run them on solar or geothermal, it's better. Today we also have better materials. We have made so much progress in the solvent, in the electrochemical, that it's actually possible to do this kind of technologies and kind of facilities today in a much faster way, because we've made so much progress in the last 20 years. Also, the context is actually also politics. You know, a lot of things are also politics, but if you think about right in the US, there's this 45Q tax credit that actually pays company $180 for every ton of CO2 that is removed by direct air capture. The CRCF in Europe is a similar thing as the nutrition label, but for quality environmental program. So as always, the market is also a big driver. There's big company like Microsoft, JP Morgan, Amazon, Stripe, Shopify, and they are all pushing to reduce their carbon emissions and improve their grades. So they're developing a lot of those direct air capture projects. So now the question we need to ask is this technology really scalable? So can we actually make those industry scalable and reduce the amount of CO2 present in our atmosphere? Let's make the calculation together. So 1 ton of CO2 requires 1 to 3 megawatt of energy. Let's make an assumption that we want to remove 1 megaton per year of CO2. That corresponds to 1 to 3 terawatt per year. And this is equivalent to 200,000 to 600,000 households power. So you can see now from this calculation that if we extract 1 ton of CO2 using direct air capture, it requires 1 to 3 megawatt of energy. It might not be very easy to understand this notion, so let's go into a feasible objective that those companies are using. They say that they want to remove 1 megaton of CO2 per year, so that corresponds to 1 to 3 terawatt of energy needed to power those facilities, those plants. And that corresponds to 200 to 600 households. So that means that actually sustainable energy like wind or geothermal to power those facilities is needed. The other point that is also good to mention is the storage. Geology is not a problem. So if we want to store the CO2 underground so it can become rocks of CO2 and then come back to nature, geology is there. The ground is ready. The problem is usually to get the permits to do this activity. Finally, there is the cost in terms of energy, but there is also a cost to extract this ton of CO2 in terms of money. So this corresponds to $600 to $1.2 thousand. So that means that it's very costly to actually extract CO2. So this number is expecting to decrease by 2030 to $200 to $400 per ton, which is more scalable and more interesting on the business side. That's very pricey, but that's exactly the same speech that offshore wind or solar were telling us 20 years ago. So that's optimistic. So here's the takeaway from this first video. Direct air capture is industrial chemistry. It's not magic. It's only viable now because we have so much more clean power than before, and so we can power those facilities using solar energy, geothermal energy, wind energy, and before the context was not right. It's also a better context because we have better chemicals than before, the policy is great, and corporate buyers are here. So it's still expensive, but it's happening. Plants are running in California, Iceland, Texas, so it's not a myth, it's reality. So direct air capture is not a silver bullet, but it's becoming a powerful tool for any emission that we can avoid. So next time in Reactor, in this next episode of this series, we're gonna talk about money. How direct air capture companies actually make money. Spoiler alert, it's complicated. See you next time.